Welcome, everybody. Hey, welcome to another episode where we ask, what's up with the universe? I'm your host, Eli Hoo, and I just want to say, yes, Mountains of Elysium, you are correct. Near black hole time is relative, so I may actually be early or late, depending on how close you are. Well, today we are going to be talking about black holes. Yes. These guys, black holes. Basically, the simplest definition, sorry, before I get into this, I want to say hi to everybody in the chat. I'm not ignoring you, so haha, you thought I was, right? Let me say hi to everybody here. Hello, Yvette. Hello, Biomike. Hello, Mr. CCDB, Mountains of Elysium, Mr. Miles. Hello, everybody. Hi, how are you guys doing today? And welcome to everybody who's watching on Rewatch. We are talking about black holes, yes. Well, at least it's not shiny and metal like Bender, Biomike. Well, today we are actually going to be talking about black holes, yes. Okay, the simplest definition of a black hole is it's an object that is so dense that not even light can escape its surface. But of course, how does that happen? I mean, the concept of a black hole can be understood by thinking about how fast something needs to move to escape the gravity of another object. This is called the escape velocity. Formally, escape velocity is the speed of an object must obtain to break free of a gravitational attraction of another body. I mean, there are two things that affect the escape velocity: the mass of an object and the distance to the center of that object. I mean, for example, as you saw in my intro, the rocket escaping. A rocket needs to accelerate to 11.2 kilometers a second in order to escape Earth's gravity. Okay, let me give you an example. If that rocket was on a planet with the same mass as Earth, but half the diameter, the escape velocity would be 15.8 kilometers per second. Even though the mass is the same, the escape velocity is greater because the object is smaller and more dense. I mean, traditionally, astronomers have talked about two basic classes of black holes. Those with masses of about 5 to 20 times that of the sun, which are called stellar mass black holes or solar mass black holes, and those with the masses of millions to billions of that times of our own sun, which are called supermassive black holes. But what about the gap between the stellar mass, supermassive black holes implies? Well, for a long time, astronomers have proposed a third class called intermediate black holes. But of course, in the past 18 years, it was hypothesized that they're starting to find possible evidence of this class of type of black holes. See, the two types of black holes, they're basically the stellar mass and solar mass black holes. I'm not answering that question, Mr. Miles. Okay, a stellar mass black hole. They are formed when a massive star runs out of fuel and collapses. They are found scattered throughout this galaxy. In the same place where we find stars. I mean, since their life began as stars anyway. Some of these stellar mass black holes, they started their lives as part of a binary star system. And the way that a black hole affects its companion and their environment can be a clue to astronomers about their presence. Supermassive black holes, on the other hand, are a whole different story. They are found at the center of nearly every single large galaxy that we have discovered. But we don't know exactly how they are actually formed. But recent studies have shown that the size of the black hole is correlated with the size of the galaxy. So there has to be some kind of connection between the formation of that black hole and the proposed galaxy itself. This is where the study of black holes comes in. People are actually actively looking at this. I mean, okay, let's take a look at the structure of a black hole itself. I'll let you take a better look right here. The structure of a black hole. There are two basic parts of the black hole: the singularity and the event horizon. The event horizon is the PNR, the point of no return, around the black hole. It's not actually a physical surface, but a sphere surrounding the black hole that marks where the escape velocity is equal to the speed of light. I mean, its radius is the Schwarzschild radius mentioned. The Schwarzschilds are compared to the center. Sorry, I'll get into that a little bit. Oh, I am not going to tell us the biggest I've ever seen. Yes, I know. Intermediary. I know. It's like the dwarf planets. Relativity is why GPS satellites have to be constantly updated as the time moves faster for them. According to the Earth is 2 years younger than the surface experience 2 years less. Yes, technically, if you live in a high-rise building, you are aging a lot slower than the people living on the ground floor. A few microseconds, but you live in a lot longer. Oh yeah, I was talking about the structure of a black hole. The event horizon. Okay, once matter is inside it, that matter will fall into the center. With such strong gravitational pull, the matter squishes to just a point, a tiny volume with a crazy big density. I mean, this point is called the singularity. It is vanishing small, so it has essentially an infinite density. It's likely that the laws of physics break down at the singularity, but we haven't actually discovered this yet. We're still discovering this. We're not exactly know what happens when we enter that singularity. But what exactly are they? Black holes are the evolutionary endpoints of at least 10 to 15 times as massive as the sun. Stars are massive as the sun. I mean, if a star that massive or larger undergoes a supernova explosion, it may leave behind a fairly massive burned out stellar remnant. With no outward forces opposed gravitational forces, this will collapse in on itself, and the star will collapse to a point of zero volume and it's so much intense density, creating what we know as a singularity. I mean, a singularity, the often term is basically referred to as a similar black hole. Spaghettified, yes. Spaghettification is a real word. You will get spaghettified when you get close, when you get sucked in. Spaghettification is a real word. I know. Spaghettified. Well, it's called spaghettification technically. So, oh yeah, I was talking about the singularity of this. Around the singularity itself, it's a region where the force of gravity is so strong that not even light can escape. Thus, we have no information that can reach us from this region, and that's why it's called a black hole. The surface itself is called the event horizon. It's the distance from a black hole within nothing can escape. In addition, nothing can prevent a particle from hitting the singularity in a very short amount of time, proper, once it has entered the horizon. Basically, the event horizon is a point of no return. But, get this, contrary to popular myth, a black hole is not a cosmic vacuum cleaner. No, it's not. If our sun was suddenly replaced with a black hole that is at the same exact mass, Earth's orbit around the sun would never be changed. Of course, our temperature would change, and there would be no solar wind or solar magnetic storms affecting us. Basically, to be sucked into a black hole, one has to cross inside the Schwarzschild radius. Basically, if this radius escape speed is equal to the speed of light. Oh, it's 667,616 miles per hour. 666,669, sorry. Many of you guys have some misconceptions about what a black hole is. I mean, check this out. Many of you guys grew up watching Disney's Black Hole and thought, okay, this is science fiction. This is science fact. Well, of course, Disney got it wrong. I mean, they had some cool special effects in 1979, granted, but the way they emphasized the way the black hole will suck you in and everything with that spaghettification was totally ludicrous, but it was still a great movie. I have not seen a video of Anton yet, but I do subscribe to Anton Petrov. He's a very cool guy. You know, people keep on asking sometimes, hang on, what's this bio mic? There's a science view. What should we call this process? Sorry. What should we call this process where an object gets long and skinny due to gravity, like spaghetti? No more like spaghettification. Yeah. Okay. I want to talk about looking for black holes. Many people ask, like, hey, if we can't see them, how do we know they're there? Well, if the light can't escape a black hole, astronomers have a nice little trick of looking for this. They don't exactly see black holes directly. Instead, astronomers observe the presence of the black hole by its effect on its surroundings. I mean, a black hole by itself without the middle of a galaxy would be very difficult to detect with anything around it. Do we see them? We do not see the black holes directly via light, but we see the surrounding light surrounding them, and I will get to that. The effects basically, okay, sorry. Astronomer, once again, I cannot talk. Why can't I talk ever again? Astronomers, yes. Us astronomers, nobody can observe a black hole directly, but we see the behaviors in objects that can only be explained by presence of very large and dense objects nearby, like light and stars and other planets and other astronomical bodies. I mean, the effects can include materials getting pulled into the black hole, to the accretion disk, forming around the black hole or stars itself. The accretion disk, it's basically a flat sheet of gas and dust surrounding a newborn star, a black hole, or any massive object going inside by attracting material. You know, since stellar black holes are small, only a few to tens of kilometers in diameter, and light that would not allow us to see them cannot escape, black hole floating alone in space would be hard, if not possible, to see in the visual spectrum. Here's an example of how astronomers find stars. As you can see, I have a lot of stars on my shirt representing the galaxy. This is a black hole. This is a black hole way over here. See this? You can't see this. This is a black hole. When a black hole passes in front of a star, the light changes and basically blocks out the light, so you can actually see a black hole passing. Astronomers have looking at the same period of sky for 8 years have discovered 2 of them like this. But they have supposed that there are millions and millions of unknown black holes out there. Let me show you this little picture here. HD 2268. I mean, the optical companion of a black hole, right here, Cygnus X1, the binary X-ray sources, are also places to find strong black hole candidates. Excuse me. A companion star is a perfect example of an falling material for a black hole. Binary system, it also allows the calculation of the black hole candidate's mass. I mean, once the mass is found, it can be determined if the candidate is a neutron star or a black hole. I mean, since neutron stars have about the same mass, about 1.5 times the mass of the sun. Another sign present of the black hole is a random variation of emitted X-rays. Kirk and tomorrow's yesterday. Black stars, I know. Why did I say black stars and black holes? Well, about the detecting with X-rays. The infalling matter that emits X-rays does not fall into the black hole at the steady rate, but rather more sporadically. Hey, I pronounced the word correctly, sporadically. I mean, this causes an observation. I can't talk again. I jinxed myself. And this causes an observation variation in X-ray intensity. If the X-ray source itself, if there's a binary star system, and we see it from certain angles, the X-rays will be periodically cut off as the source is eclipsed by the companion star. I mean, when looking for black hole candidates, all things are taken into account. Many X-ray satellites have scanned the skies for X-ray sources that might be black hole candidates, like Cygnus X1. Cygnus X1. This is a cool little star. It's the longest known of a black hole candidates. It is a highly variable with irregular sources with X-ray emissions that flicker in hundredths of a second. Hawking radiation, yes. Hawking radiation was this. Sorry, I didn't cover Hawking radiation. I'm going to put that in my little notes right here. I'm sorry about that. I'll put it in the, okay. I'll put the information from JPL and from MIT about the Hawking radiation in the description of this video so you guys can read up on Hawking radiation. MIT has a very descriptive little page with not that many highly calculable notes like calculus on there so you can understand this, but it breaks it down. I'll link it in for the at the end of this video for you guys about Hawking radiation, okay? Sorry about that. Where was I? Oh, Cygnus X1. I was talking about the variable and irregular sources. An object, it can't flicker faster than the time required for light to travel across the object. In a hundredth of a second of a light, travels 3,000 kilometers. This is only 1/4 of Earth's diameter. So the region emitting the X-rays on Cygnus X1 is very, very small. Stereoscopic observations show that the spectral lines of the companion star HTE 226868 oscillates for the period of 5.6 days from the mass of luminary radiation. I mean, the mass of the supergiant is calculated as 30 times the mass of our sun. No, I am not wearing a flag. I am wearing my star shirt. Because I'm in the field of stars, see? I do not have a flag shirt, by the way. Right now, we only know about 20 X-ray binaries known with black holes from the measure of black hole masses. The first of these is an X-ray transient called A0620-000. Sorry, that's 00. 2 zeros, not 3. It's A0620-00. That's a star call. It was discovered around my birthday in '75. Yes, I'm old. And of course, the mass of the compact object was determined in the mid-'80s to be greater than 3.5 solar masses. I mean, this very clearly excludes a neutron star, which has a mass of about 1.5 solar masses. Let's see. Striped underwear. I'm not wearing any underwear. I mean, striped underwear. Oops. Burgundy slip. Not fair. If Mike gets a cookie, I want one too. What kind of cookies are you having? Are you having chocolate chip? I'll take anything chocolate. You guys want to know exactly what a black hole looks like? Well, in 2019, astronomers using the Event Horizon Telescope, the EHT, was an international collaboration that networked 8 ground-based radio telescopes into a single Earth-sized dish. I mean, they captured an image of a black hole for the very first time. As you can see, it will zoom in. This is the Hubble Space Telescope visible and Chandra X-ray, observatory X-ray composite images right here. This appears as a dark circle silhouetted by an orbiting disk of hot, glowing matter. The supermassive black hole is located at the heart of the galaxy M87, located about 55 million years away, and weighs more than 6 billion solar masses. Its event horizon extends so far it would encompass much of our solar system out to well beyond our planets. This is from the Very Long Baseline Array radio telescope. And this is what they caught. The very first image of a black hole. Here's a little comparison to our own little solar system. This is the event horizon. Let's get a better look at that little, the actual size of the black hole itself. I mean, the first picture of the black hole, it showed the bright ring formed as light bands. The intense gravity around the black hole is 6.5 billion times the sun's mass. As you can see in the diagram here, Voyager 1 would barely be on the edge of the event horizon of the black hole. It would barely be there. This is how huge this thing is. I mean, another important discovery. Universe is beautiful. I mean, another important discovery related to black holes. came in 2015 when the scientists first detected gravitational waves. I talked about gravitational waves on my show on my show a few weeks back. They are ripples in the fabric of space-time, predicted a century earlier by Albert Einstein's general theory of relativity. The LIGO actually detected these waves from an event called the GW 15914, where two orbiting black holes spiraled into each other and merged approximately 1.3 billion years ago. Well, since then, LIGO and other telescopes and facilities around the world have observed numerous black hole mergers via the gravitational waves they produce. I mean, there are new methods, but astronomers have been studying black holes through various forms of light they emit for decades. Although light cannot escape a black hole's event horizon, that enormous tidal forces in its vicinity causes nearby matter to heat up to millions of degrees and emit radio waves and X-rays. I mean, some of these material orbiting even closer to the event horizon may be hurled out, forming jets of particles moving at the speed of light that emit radio waves and X-rays and gamma rays and stuff that makes a boost ground into a Hulk. Yes, gamma rays. I said gamma rays. I mean, the jets that can ascend from these supermassive black holes can ascend for hundreds of light years into space. I mean, radio data from the NSFL VLA, I'm sorry, I'm abbreviating again, NSF, the National Science Foundation, and a Very Large Array facility. It was basically used to construct an image of Cygnus A. It's the brightest radio source in the sky located inside our own galaxy. Yes. Long, thin particle jets produce a supermassive black hole in the galaxy center. Like vast loads of speeding electrons trapped by magnetic fields, the radio waves. I mean, from tip to tip, the structure spans about 500,000 light years. NASA's Chandra, Swift, the New Star, and the NICER space telescopes, as well as other missions, they are continuing to take measurements of black holes and their environments so we can learn more about these crazy little things up in space. If you want to check out some of the recent findings about establishing the origin of solar mass, black holes, and the connection to dark matter, check out an article I linked in the description below. You might have to refresh it. It's from Calvi, Institute of Physical and Mathematics of the Universe. The large black hole is less violent than the horizon, is making it more likely you could pass that issue. Possibly. Possibly. Oh, some of you guys might be wondering, did I mention that a supermassive black hole was heading at Earth's way at 110,000 kilometers per second? Yeah, I did. We have a black hole heading toward us right now as we speak. There's a massive, huge black hole with millions of times more mass than our own sun is plunging toward Earth. But it's not going to come right now. It'll be here in about 4 billion years. What I'm talking about is Andromeda. Yes, Andromeda, supermassive black hole, is colliding with our own Milky Way galaxy in about 4 billion years. So we're going to be safe for now. I'm not sure, Mr. CCDV. Mustard is very good. So explode before Andromeda gets us. No, our sun is expected to explode about 5 billion years from now. And Andromeda will be formed in about 5 billion years, but it'll be colliding with us in about 4.5 billion years. So basically, by the time the sun heats up, about 4.5 billion years from now, by the time our sun heats up, we're going to be a molten planet. There's going to be no life left on Earth that we recognize within about 4.5 billion years. But Earth itself is going to be destroyed eventually. And that's in another story. Well, I want to thank everybody for joining me today as we talk a little bit about black holes. Yes. So if you haven't already read that subscription button, please do. If you like what you see or you got any comments or questions, put them down on the thing and I will respond to almost every single one I can. Like I said, almost every single one I can because I do have to do something called sleep. Sorry. You saw it on Doctor Who. Well, that was that theory, though. Okay. There was many theories about what's going to happen to our own planet when the sun goes supernova, sun explodes. There's a theory that the gravitational pull of the sun will push Venus toward Earth, and Venus will crash on Earth. There's a chance that Venus gets swallowed up and it'll push Earth, and it'll push Earth out, or Earth will stay present, and the sun will go up Earth, engulf Earth. I can't talk. There's many hypothetical theories about what's going to happen. We don't know. Yes, I agree. It'd be more like a dance on a collision. There is very little chance that two stars will come together. There, like I said, space is so vast, like an asteroid field. If you watch a movie with an asteroid field, that is not an asteroid field. A real asteroid field is you're at an asteroid, you look around, you don't see another one, or you see a small little tiny little light of another one. That's an asteroid field. What they're actually in is a rubble field. I call those good movies with bad sci-fi. And hello, Mr. CCTV. Hello, Mr. Jedi Bell. Glad to see you here. And I just want to thank everybody else again for joining me, and everybody else around here. So I hope everybody has a good day. So you guys look up at the stars, maybe wondrous things out there if it's a clear sky, and enjoy the rest of your day.